Hello, this is Matthew Feingold. This is my Capstone Research Independent Study presentation for DePaul University. Um, my topic was on bump mapping, so let's get into it. Bump mapping refers to a collection of texturing techniques that produce a more three-dimensional appearance than regular texture mapping. Um, There are a few types of bump mapping that I'll talk about. Normal mapping is kind of the most base one that's kind of used for all of them. Um, then parallax displacement mapping is a type of height mapping that is an approximation. I'll get more into that. And then parallax occlusion mapping is the more accurate version of that. So normal maps are textures. This image here, the blue, mostly blue image here, is a normal map. Um, and what it's used for is to take a low polygon model, such as this surface here on the left side, one face of a cube, um, and use this normal map to calculate the lighting as if it had more complex geometry. So we can see on the left side it looks like a flat image, and on the right side it looks like there are little divots separating all of the bricks, and that's due to the normal map. There's no extra vertices in the geometry here. Um, so normal mapping is essentially a lighting trick. um, So without normal mapping, the polygons, the triangles, each vertex of the triangle stores the normal, um, and that normal is interpolated across the triangle during the pixel shading routine and basically used across the flat triangle. So there's not any real um, like differentiation in the surface normal across the triangle, whereas with normal mapping, you sample the normal map at every pixel across the triangle instead of just interpolating, so you get more of a granular control, um, allowing for the more accurate lighting that you get. So here's another example of the light kind of hitting a surface with the normal map versus without it. Um, so normal maps are stored in the texture as color. So every texture has RGB, red, green, blue, alpha data, and that actually directly translates to our XYZ W normal. But let's forget about the W for now. So how we do that is colors are in the range of 0 to 1 in our texture, and our normals are in the range of -1 to 1 because they could be pointing off to the left or to the right. Um, so in order to kind of rescale our range here, we multiply our extracted RGB um, color data by 2, and then we subtract by 1. So that will basically double the range and then subtract by 1 to give us the range from -1 to 1. Um, and then that's how we get our normal directly from the normal map. So if you look at this, the blue color, which would be 0, 0, 1, if it's a pure blue RGB, is sticking straight up because it's the Z axis, XYZ, the blue, RGB, XYZ, the blue corresponds to the Z. So you can kind of take a look at the color here and see which way these surface normals are going to be pointing. um, so with normal mapping, you need to, with lighting, you need to have all of your vectors and matrices in the same space. So you might do your lighting in camera space or in world space or model space. Um, and regularly, when you're doing your lighting, your normal that you get, um, you have it in maybe model space, or you transform it into whatever space your camera vector and your light vector are in. But with normal mapping, the light or the normal stored in the normal map comes out in surface space or tangent space. So we have two options here. We can either transform the surface normal into the same space as the light and camera vectors, or we can transform the light and the camera vectors into tangent space or surface space, which is the space that our extracted normal from the normal map is in. So there are some performance considerations, depends on the number of lights and number of vertices and everything, um, but those are our two options. So let's talk about tangent space now, the surface local space. Basically, if you think about this pink line here as the surface of one of our triangles, the regular surface normal would be this blue vector here sticking straight out of the surface at a 90-degree angle to the surface. But the normals extracted from the normal map may be perturbed here, and all of these dotted line vectors are examples of what you could potentially pull out of the normal map. So, um, basically, we need to calculate a matrix that represents this surface local space. So here's our normal map texture, kind of rotated in 3D space here. And we have, this blue one's maybe kind of hard to see, but we have these three vectors. Sorry, excuse me. We have these three vectors here. The tangent vector runs along the x-axis, or the u, if you're thinking UV texture coordinates of the texture. The bitangent vector runs along the y-axis of the texture. And the, or sorry, the bitangent, yeah, bitangent vector runs along the y-axis of the texture. And the surface normal runs along the z here. So we essentially need a orientation matrix to translate, or not translate, to transform our either our surface normal into a different space to correspond with the light and camera vectors, or get the camera and light vectors into surface space. So here, let's talk about calculating this matrix. What we need is called the TBN matrix, which is a matrix comprised of the tangent, the bitangent, and the normal. Right here, I'm showing it in column major, but depending on what translations we're doing, or transformations we're doing, we might want it in row major, which would just be the transpose. Transpose and inverse are the same. We'll talk more about that later. Transpose and inverse are not the same. They're the same in this situation because the matrix is orthogonal. But anyway, so we need this matrix. So let's get to it. We can start out by by defining our variables that we need for this equation to calculate our matrix. So in this triangle here, let's just say this is our given triangle we're working with that we want to render. We have 3 points, P1, P2, and P3. Those have x, y, z coordinates for position. They also have UVs, which are the texture coordinates associated with them. So we have U1, V1, U2, V2, etc. And then we have our two edges of the triangle here, edge 1 and edge 2, which we can calculate by subtracting the points. So P1 minus P2 will give us a vector pointing from P2 to P1, so that's our edge 1. And then P3 minus P2 will give us this edge 2 vector. Then we also have our delta U and delta V's that correspond with the edges. So in the same way that we have our edges corresponding to our positions in 3D space by subtracting these XYZ points, we can subtract our UV coordinates. So basically here the diagram here shows the delta UV for the edge 2. If we subtract the U3, which would be the x coordinate here, by the subtract u3 and u2, we get this difference here. And if we subtract the v3 and the v2, we get this difference here. And then we would do the same for the other edge. So we have these two delta UVs. Um, and now we can basically calculate these edges, edge 1 and edge 2, in terms of the tangent and the bitangent, which are what we want to solve. This axis here, the tangent, and the bitangent is the green y-axis. So here are our two equations, delta u1 times tangent plus delta v1 times bitangent. I won't read out the second one, it's written right there for you, but here we have two equations that define our edges, and when we have two equations and our two unknowns, tangent, bitangent, but the rest we know the edges, the delta u, v's, we can do some algebra to solve for our two unknowns. So here I just rewrote the edge equation from the last slide up here, and I'm going to kind of just go through the steps to show how we solve for the tangent and the bitangent here. So here in this one I expand out all of I expand out the edge, the tangent, the bitangent here to make it more visible. And here I just write it out as matrices, so I kind of, I'm not going to go through all the steps, but basically we can end up with this equation here with our matrices. We have our edge matrix, our delta UV matrix, and our tangent bitangent matrix. So here's that equation up here again, the top. So in the end, we want our tangent and bitangent. So we can, to solve for that, we basically want to isolate this equation. So we can take the inverse of the UV matrix and multiply it by each side in order to isolate this matrix. So now we have the inverse of the delta UV matrix times the edge matrix is equal to the tangent bitangent matrix. And I down here expanded out the inverse here because in the end what we're going to want to do is actually just extract the tangent. The bitangent can be solved by doing a cross product in the vertex shader, so we don't exactly need to solve for it now. We can save some time in our CPU processing phase. So, or not, sorry, in our CPU processing phase where we grab the tangent. So, so for the tangent, we basically just extract the part of this operation, this mathematical multiplication. We just extract the part where we're calculating the tangent. We don't care about the bitangent part. So after doing some simplification here, we end up getting this these three equations to calculate the x, y, and z of the tangent. And maybe I hope I made this clear before, but what we're doing right now is we're calculating the tangent on the CPU and sending it as part of our vertex to the GPU, so that in the vertex shading routine we can use it to quickly calculate the bitangent using the tangent and the normal. If we cross them, we can get the bitangent. And then with those three, the tangent, the bitangent, and the normal, we can get the TBN matrix and use that to transform our vectors. So anyway, sorry if that wasn't clear before. So now we know how to get the tangent. We have these three equations that get us the x, y, z of the tangent. So we can use those to pass the tangent of each triangle. Remember, each triangle has the same tangent, so when you're calculating these, you'd be looping over all the triangles in your model and storing the tangent, the same tangent in each of the 3 points for the triangle. Anyway, so now we have the TBN matrix. So right here, how I display it is row major, where the tangent, the bitangent, and normal vectors are stored in each row of the matrix. And if you have it this way, it will transform matrices from whatever space the tangent, bitangent, normal are defined in. So if these are in model space, It will transform vectors and matrices from model space into surface space if you do the multiplication. If you were to get the transpose of this and have a column major TBN matrix where the vectors are the T, the B, and the N are in the columns, it will transform vectors, matrices out of surface space and into model space or whatever space the vectors are in. And I wanted to point out that in GLSL, when you define your mat3 matrix type, um, it will construct a column major matrix. So it's important to remember kind of how your transformations are working there. Um, so here's just a couple final little examples of how normal maps are kind of working. Here's a picture of, or screen grab of the of this 3D model with really high poly count. Here's a simplified mesh with much less triangles. And here's the rendering of the simplified low-res polygon or low-res model with the normal mapping. And you can see it looks very similar. So it saves a lot of processing time because you don't have to translate and rotate and basically process all of these different triangles. And here's just a few more images. And I'll show this in my implementation. So here I have a cube. It's got no normal mapping. It's just got some blend-fong lighting on it. It's just a simple cube with the image on it. And I'm going to turn on the normal mapping now. And we can see that there's a lot more detail in here. It looks much more 3D. And but we're still using the same number of triangles, just 2 triangles per face for this cube. And the lighting is being calculated using the normals. Okay, so let's move on to height mapping. Height maps are grayscale textures, which is this one in the top left, and it basically is a value from 0 to 1. In grayscale textures, all of the RGB values are the same. So when we end up sampling this, we can just sample like the R channel, for example. But the height color basically says 0 is like surface level, no height, and that would be black on this image, and then white is as high up as you can get. So we can basically sample at each pixel just like we do in the normal map to grab the height. And we don't need to change the range like we do with the normal map for the height map. So parallax displacement mapping is a method of height mapping that is an approximation. There are some issues with it, but it's relatively easy to implement, and if you kind of mess with your scale and bias, these tweakable values, you can get some nice results. So I'm going to open up this paper. This is what I referenced a lot to learn about this, and I just wanted to kind of go through this a little bit. So the height mapping is going to give us a more kind of 3-dimensional look where we have some of the bricks here kind of blocking our view of the ones behind them. So essentially what this does, I'm going to look at this diagram here. This is the ideal diagram of what we're working with. What we're actually going to do is an approximation of this. But so here, this line across the bottom is the surface of our polygon, surface of our triangle. This thick black line represents our height map. So at every position across the surface of our triangle, there's some corresponding height we can extract from the height map. So that's what this represents. So this T actual, this is our actual texture coordinate of the current pixel we're trying to render. And what we can do is sample the height at that current pixel, and and that's what A is here. So the idea behind this technique is to shift the texture coordinates that we use to render based on the the view vector, or the I vector, and the height. So if this is our camera right here, and we're looking down at the surface of this triangle, um, we're not actually going to see this part if we pretend that this thick black line is our actual model here. We're not going to see this part here. We're going to see this part here. So we actually want to render the uh, the diffuse texture and the our specular map and all that stuff. We want to use the texture coordinates for this spot. So essentially, what we can do is shift the texture coordinates over. And that's the basic idea of height mapping, is we use this I vector to look at the surface and see what part of the surface are we actually looking at. And then we use those texture coordinates. So that's the ideal way to do it. But that takes some processing to do. So this approximation is pretty quick and simple, but it's an approximation. So um, just right off the bat, before I get into it, we can see that the new offset texture coordinates that we would get from this formula are over here. If you remember from this one, we want it to be where the I vector intersects with the height map. Well, the I vector intersects with the height map right here. So ideally, we would want this texture coordinate right here, but we're getting this one. So it's an approximation. It's not exactly accurate. And if you end up having too steep of drop-offs in your height map, you can get artifacting and texture swimming issues that are just bad. So essentially, this is the equation to calculate it. Okay, so we have the original, or no, sorry, the new texture coordinates are equal to the original texture coordinates plus the offset. And to calculate the offset, the what this paper is actually doing is explaining a new way to calculate the offset. This is the original one, which basically takes the height, which he's scaled and balanced by, or scaled and biased by tweakable values, which it explains up here, and then multiplies the height by the view vector, which is that I vector that we looked at earlier. Takes the xy, divides it by the z. We're dealing with like these 2D coordinates, the 2D texture coordinates, so we don't quite care about the z. But what this paper suggests is limiting the offset here to basically limit it to the height. So when we do this division, this I vector is normalized first. So the z value is going to be 1 or a fraction, something between 0 and 1. So when we do this division, we're either keeping this value the same, or we're making it bigger. So this offset becomes bigger when we do this, potentially. His new way basically says don't do the z division, and we basically say scale it by the height. So we normalize this, and then we scale it by the height. And sorry, I have a bit of a cough. And so basically what this does is gives us kind of less extreme offsets to our texture coordinate offset. So if we have bigger bigger variations in our height map, like sharper, steeper cliffs and stuff, we won't have quite as many artifacting issues. But anyway, that's kind of all this is doing. Oh yeah, one thing I need to mention is that the I vector needs to be in tangent space when we're doing this. So if you are doing this parallax displacement mapping, it might be a good idea to do your normal mapping in surface space and move your camera and light vectors into surface space, because you need your camera vector in surface space for this already. So that's what I did. And I can give a quick demonstration. I purposely set the scale so we'll see some of the artifacting, but here's the displacement mapping. You can see some of the artifacting around the sides here. This height map that I'm using for this is probably not necessarily meant for this technique. If I turn the scale down, it's less of a dramatic visual result in terms of the height, but we eliminate the artifacting. But if you want to do a quick comparison, this is normal mapping. This is the height mapping. Normal mapping, height mapping. And yeah, this is the parallax displacement mapping. This paper did a nice job of explaining it. But there is a way to get closer to this ideal texture coordinate offset, and that is going to be relief mapping. So relief mapping is the much more convincing way. Here on the left, here we have the parallax displacement mapping that I just showed, and on the right is the relief mapping. So notice at the top of this cube here, the shapes are much more pronounced. They look much more, there's much more height to them all across, but it's especially noticeable on the top, and I guess on the side there too. Here's the difference between normal mapping and relief mapping, just to show how extreme that is. Here's an example of relief mapping from the game Crisis. That's how they do all these rocks here. And so, okay, how does relief mapping work? So, similar to our previous diagram we looked at in that paper, this bottom here is our actual surface of the triangle. The blue represents our height map, and the green vector is our camera or eye vector from the position, from our actual position that we're trying to render to the camera. So instead of doing the offset approximation, relief mapping actually samples the eye vector and calculates a more accurate like first intersection of the camera and the height vector. So there are a few methods, but just one of them is binary search. You basically, set certain samples and search and cut in half and do the logarithmic binary search to grab this. Anyway, I don't have a working example of it because it's much more complicated. I didn't get to it, but this is the idea behind it. And so future research that you could kind of go from here is physically based rendering, which basically is a mathematical model of real world like materials and applying that to rendering in order to create a much more convincing like photorealistic rendering of your models. So it uses mathematical models for roughness, metallicity, sorry, I don't know how to pronounce metallicity, glossiness, etc. And you can, a lot of these use textures just like the height map and the normal map, but you store them in like a roughness texture and a metallicity texture and so on, and you can use these to kind of tweak the material properties of your model or of your texture rendering. I know Unity Engine, Real Engine are using these and have nice like GUIs to show how that works. And then this book seems to be very popular for learning physically based rendering. Anyway, that is my presentation. Sorry it maybe ran a bit long, but anyway, thank you for watching.